Our speaker this morning is Dr. Nathaniel Ferraro, who works with the Princeton Plasma and Fusion Laboratory in Princeton. And on his way up this morning from Princeton, he got away from home and smelled a little gas driving his vehicle, and then saw a little smoke coming up and figured it might be a good idea to pull over to into a service station, where they opened the hood and found that his fuel line had been chewed by a squirrel, and gas was pouring out onto the block of the engine of the car. And the mechanic assured him that if he'd kept going, there would have been a fire. So Nate had to call his wife, who was home with the 3-year-old, and have her bring the other car up to him. And not sure how she got home, but anyway, Nate is a principal research physicist and deputy head of the theory department at Princeton Plasma Physics Laboratory in Princeton. Dr. Ferraro received a BA in mathematics and physics from Dartmouth College in 2002 and a PhD in plasma physics from Princeton University in 2008. And after receiving his PhD, he worked at General Atomics in San Diego, California, which hosts the D3D National Fusion Facility, before returning to Princeton in 2015. In addition to his research focusing on computational modeling of fusion plasmas, Dr. Ferraro has been active in strategic planning, serving as co-chair of a major recent community-wide fusion planning process. Nate, welcome to the old guard.
Thank you so much, Ian. Let me share my screen here. I'm really glad to be here, considering the alternative. I made it the rest of the way in an electric car, which I highly recommend. No fuel lines in those. So I'm here today to talk about something that's been in the news a lot. You might have heard some of the stories here. I'm having trouble advancing. There we go. So fusion energy. This has been in the news an amazingly large number of times in the past year or so. You might have seen some of these headlines. It's been actually making headlines in mainstream news. Fusion startups are now raising billions of dollars. The Biden administration recently announced at the White House a bold decadal vision for fusion energy. When I tell people at a party that I do fusion, it used to be that they would sort of nod and excuse themselves to get a drink. And now they actually tell me something that they've read in the news, something that sometimes I haven't even heard of myself. Now it's me who's having to excuse myself to go get a drink sometimes. People are really interested in this, and I think there's a good reason why. So what I'm going to try to convey today is what is going on with fusion energy research? Why is it making into the news? And what are the prospects for fusion? Now, as a warning, this isn't the talk that I typically give. Normally, I'll be giving a talk at a scientific conference talking about experimental data and results, but I hope this is clear and informative, and I'm happy to have a conversation after this and answer any questions you might have. So let me start with some of the basics. What is fusion energy? I know many of you will have heard of this. Fusion is the process that powers the sun and the stars. So it is a nuclear process where light elements fuse together and are combined into heavy elements. And in the process, it releases a lot of energy. This is essentially the opposite of nuclear fission, which is the basis for nuclear power plants that exist right now. So nuclear fission, in that process, you take a heavy element like uranium, you split it into lighter elements. So the actual physical process of fusion is well understood. That's not what we're researching. We're researching how to take this and actually develop it on Earth as a power plant on Earth. So fusion, if we can get it working, is a near ideal power source. It doesn't generate CO2 or any greenhouse gases. It doesn't generate any high-level nuclear waste like fission does. There's no possibility of a meltdown. The fuel is abundant and available to all nations, and I have a little asterisk there because I have to qualify that. but it can be extracted from seawater. A gigawatt scale fusion reactor is just burning a couple kilograms of this fuel per week. And it provides a clean source of base load power. It's power that's localized, it's always going to be on, it's dispatchable. So that sounds great, but the problem is fusion is very hard to do. So fusion requires very high temperatures. The center of the sun is 15 million degrees. The center of a fusion reactor has to be more than 100 million degrees. So that's obviously a challenge. And this is the fundamental challenge of fusion research. How do we keep the temperature of the plasma so high without spending more energy than we're actually getting from the fusion to heat the plasma? So this is what we call the confinement problem. How do we keep that heat in the plasma without letting it leak out, without melting things that we're using to confine it? There's other questions we have to answer too. Where do we get the fuel for it? And again, I'm going to describe that in a slide here. How do we operate reliably in the presence of high heat fluxes and neutron fluxes? So the fusion process is releasing neutrons. This is creating a hostile environment for many materials. And the question for making this into a power plant is, how do we take all this and make it into a system that is economically competitive with other sources of energy? So let me talk about the fuel that fusion uses. So a power plant is probably going to use a mixture of deuterium and tritium. So these are isotopes of hydrogen. Deuterium, if you can see this picture here, is one proton, which is the blue one, and one neutron. So it's like hydrogen plus an extra neutron. Tritium is the same thing, but another neutron, so two neutrons. Deuterium is plentiful. It can be extracted from seawater. Something like 1 every 1,000 atoms of hydrogen is actually a deuterium atom. And there's basically inexhaustible source of that in the water. Tritium is very rare. It has a half-life of 13 years. It must be manufactured. Now, we know how to do this in principle. But any kind of commercial deuterium-tritium reactor is going to have to breed tritium. And this is a technology that hasn't yet been demonstrated, along with a few other technologies that I'll mention that have not been demonstrated. So what do we do when we're doing fusion research? Well, plasma physics, as Ian said, I'm from the Princeton Plasma Physics Laboratory. Plasma physics is really central for fusion research. So at the temperatures that I just talked about, electrons become untethered from their nuclei, from the positively charged nuclei. So you can see here's what a gas would look like if you looked really close. You have the positively charged nuclei, and you have these little black electrons that are tethered to the nuclei. Once you heat it up, the electrons lose their bonds to the nucleus, and you have basically two independent gases of positively charged nuclei and negatively charged electrons. So plasmas are a lot like gases, but they're very good electrical conductors. This means they respond to magnetic fields, and they can carry very large electrical currents. And you can see in this little plasma ball, you have a charged electrode at the center, and you have these currents that are flowing from the center to the edge, and that's what's causing the plasma to glow up there. You have electrical currents flowing in the plasma. So, because basically any method of getting fusion is going to require these high temperatures, basically anything that is going to be fusing is going to be plasma. So plasma physics plays a central role in fusion energy research. And this is the kind of thing I would be showing if this were a scientific conference. This is actually taken from a slide. Yeah. Oh, thank you very much for alerting to me that. I'll correct that. So just so you guys know what I'm talking about here, this is a simplified model of a plasma. This is called, I won't show the more complicated one. This is magnetohydrodynamics. This is a model that we use to simulate the large scale stability and properties of a fusion plasma. Plasma physics is notoriously complex. It's very difficult to make progress with pen and paper theory on these kind of equations. People have done it. There have been very, very smart people in the field, and I'll talk about some of them. But really, to make progress with these kind of equations, we need computers, we need supercomputers. And the progress we've made in computational resources over the past couple of decades has really actually accelerated our progress towards fusion energy. Okay, so what do we actually do to get fusion? There's two main approaches. One is called inertial fusion energy, and this is where you have a small pellet of this deuterium and tritium gas, maybe that's been frozen, and you blast it with lasers. This causes that pellet to compress. You get very high pressures and very high temperatures because of that, and you get a burst of fusion energy. The other main approach is called magnetic fusion energy. This is where you have, as I mentioned before, plasmas are electrically conducting, they respond to magnetic fields. So you can actually confine plasmas using magnetic fields. Most magnetic fusion energy research focuses on this approach, and I'll get a little bit more into that, the types of magnetic fusion devices in a minute. So how does magnetic confinement work? A magnetic field permeates all space. It can be visualized as lines running through the space. What happens when you get a charged particle that's moving in space with a magnetic field is that particle can't just move straight anymore. It actually will start to spiral around that magnetic field. So those particles can move along the magnetic field, but they can't really move across those lines. They can't move across those lines of force, because as soon as they start doing that, they'll spiral and stay attached to that magnetic field line. So what we can do is we can arrange these field lines to cover a surface. And that keeps all the particles trapped on that surface or within that surface. It turns out that the simplest surface you can make with magnetic fields, because of properties of the magnetic fields, is a torus. So you'll often hear about toroidal confinement. These are tokamaks, these are stellarators. I'll explain these in a minute. But these are magnetic fields arranged in nested toruses to keep the plasma confined. Okay, so there's two main types of magnetic confinement facilities. There's more than this, but these are the main ones that we have put most of our resources into. There's tokamaks, this one on the left. These were invented by the Soviets. This is a Russian portmanteau of toroidal magnetic field. In tokamaks, tokamaks are very interesting, because you have to drive an electrical current inside the plasma, and that electrical current makes a magnetic field that confines the plasma. So the plasma is confining itself through the electric currents driven in the plasma. These turn out to have excellent confinement, but they're prone to instability. If something perturbs that plasma current, that electrical current, you can lose the confining magnetic field, you can lose confinement of your plasma. On the other hand, we have stellarators on the right. In this case, we don't depend on currents that are driven in the plasma. All the magnetic fields are created by magnetic coils that are represented in blue here. These are very stable because we don't worry about plasma instabilities in that case. They're inherently steady state. The problem is the coils tend to be complicated, and the confinement, so that's how well is trapping the energy in the plasma, tends not to be as good as in tokamaks so far. So here's sort of a schematic overview of what a fusion power plant might look like. So this is taken from the website of a private company, Commonwealth Fusion Systems, which is actually in the midst of designing something like this. So what you have is an inner chamber that is filled with deuterium gas, deuterium and tritium gas. Let me hide this here. There we go. So this chamber is filled with gas. The plasma is created and heated using microwaves usually. There's other ways of heating it, but that's usually the main way of heating it. And fusion, hopefully, if you've done your job in building a good confinement device, fusion will start. So this is the deuterium and the tritium gases will start to merge and form helium and neutrons. And these are very energetic particles. These helium nuclei, which are also called alpha particles, are charged particles. So they're also confined by the magnetic field. They don't escape. They actually stay confined, and they interact with the plasma, continuing to heat the plasma. The neutrons that are released are not charged. Those are neutral particles. So they are not affected by the magnetic field. They stream right out of the device and they hit the blanket out here. So the blanket has two purposes. One is to breed tritium. So if there's lithium in this blanket, it can actually be producing tritium that you can use as your fuel. The other purpose is it heats up, and then you can create power with it just like you do in any other power plant or with a thermal interchange. So there's one more concept to describe here to understand how well your fusion reactor is doing, and that's fusion gain. So fusion gain describes how much energy is coming out relative to how much is going in. If you want a power plant, fusion gain has to be greater than 1. You have to be producing more energy than you're using. That's the fundamental condition for a power plant. So Q can mean different things in fusion. There's what we call Q scientific, which is how much energy is coming out of the plasma relative to how much is going into the plasma. And then there's Q engineering, which is how much energy you're putting onto the grid relative to how much energy you're pulling off the grid. And these are different things, because once you pull that energy into the grid for running your heating systems, your magnets, your fuel processing, for running the vending machine in the hall, the lights in your building, there's losses that aren't going into the plasma. So the amount of energy you're putting into the plasma is less than the amount that's coming into the facility. And then similarly, when you do your power conversion, you're losing energy. That's not going to be 100% efficient system. So really, Q scientific greater than 1 is good, but for a power plant, you need Q engineering to be greater than 1. In scientific literature, if you ever see, or in the mainstream media, if you see something that says fusion gain, they're probably talking about Q scientific. So the gain just of the plasma. Nobody can quote any numbers for Q engineering because nobody's built a power plant yet. Okay, so a brief history of fusion energy research. So probably the start of fusion energy research begins in 1951. This was Project Matterhorn, which started at Princeton. This project was divided into 2 parts. There was Matterhorn S for Stellarator, and that was for fusion energy research and led by Professor of Astrophysics Lyman Spitzer. And then there was Matterhorn B for bomb, and that was for other purposes led by John Wheeler. In 1958, Matterhorn B was brought to a close. That mission was successful. We had successfully built thermonuclear weapons. Fusion energy research was proving to be harder than the weapons research. So at that point, they declassified the fusion energy research. They realized that we were going to need participation from the whole world to accomplish this. So it was declassified. We started working with colleagues in other countries. In 1961, Matterhorn S became the Princeton Plasma Physics Lab, which it still is today. And you can see here, this is Lyman Spitzer, and this is a very early concept of a stellarator. And then in the 1970s, things started to change. So the very early attempts, as I mentioned, at fusion energy were kind of disappointing. It was much harder to get confinement than we had thought. But then in the 1960s, the Soviets developed this concept of the tokamak, which I've explained. This changed things dramatically. Tokamaks have excellent confinement compared to those early stellarators. So you get much hotter plasmas given a much smaller energy input. And you can see, once this happened, this sparked tokamak experiments around the world. More and more investment was put into these tokamaks. So these blue dots are all different tokamaks that were built starting. So T3, this is a Soviet tokamak built back in the late 60s. And a number of these here are built at in the United States, in Japan. If you look at this metric for confinement, the confinement in tokamaks is actually outpacing Moore's law. So here we have the plot of the number of transistors in semiconductors. You can see this red line is what is referred to as Moore's law. And for comparison, you also have the energy in accelerators for high energy physics research. So tokamak confinement was outpacing Moore's law, which is amazing. Now you notice this plot for tokamaks ends in 1997. The Pentium 4 was not the last microchip that they made. This, if you look at what happens with Moore's law, this has continued almost to the present day. That's not the case for tokamaks, and I'll explain why. So in the 1990s, fusion falls short. So because of this, these impressive results with tokamaks, 2 large tokamaks were built in the 1980s, unofficially with a mission to demonstrate Q scientific greater than 1. Unlike, and these 2 tokamaks were on the top here. This is the tokamak fusion test reactor at PPPL, TFTR. And this one on the bottom is a cartoon drawing of the Joint European Torus jet in England. So unlike the previous tokamaks that had been constructed, these tokamaks actually used tritium. All the previous tokamaks had just been using deuterium because deuterium is cheap and plentiful. These actually got a hold of some tritium, and were using tritium to see how much fusion energy they could actually produce. So both of them failed to achieve Q greater than 1. I wouldn't say they were unsuccessful experiments. We learned a lot from them, but they did not achieve this basic requirement for a power plant. So TFTR achieved Q of around 0.3 in 1994. JET achieved Q of around 2/3 in 1997. TFTR was decommissioned in 1997. JET remained operational, but would not run again with tritium until a few years ago. So why did these not work? One of them was the issue of turbulence. This is a major focus of plasma physics research. The plasma needs to be 100 million degrees at the center, and it needs to be a couple hundred degrees at the edge for any material to survive it. Whenever you have a big gradient in the temperature like that, you're driving instabilities, you're driving turbulence. And this, it turns out, you lose a lot of energy due to the turbulent convection that you get because of this. Another challenge, this is especially true in JET, is not just this microturbulent convection, but you have issues with large-scale stability in tokamaks, as I described before. If you have a change to the current in the plasma, you can suddenly lose confinement of your entire plasma. That's not good for a tokamak. It's not good for a power plant for sure. You don't want to be losing your energy. And it actually, if you're not careful about it, you could damage your device. And you can see a picture of this happening. This is in the Tor Supra device, which is a tokamak in France. You can see a disruption happening. During this disruption, you get a beam of high energy electrons that's formed, and you end up melting the wall. So these are things, as you scale up a tokamak concept, you start to run into problems with this. So this is something that any tokamak fusion reactor design will need to avoid. Okay, so TFTR and JET were not successful in demonstrating Q greater than 1. In the 90s, after those attempts were made, it was clear to the community and to Congress that innovations would need to happen for this to succeed as a power plant. So the U.S. fusion program research pivoted towards scientific understanding. So it moved away from a directed energy mission towards a mission of scientific understanding, making sure we really understood what was going on in the devices before we made another shot at energy production. Accordingly, budgets dropped fairly dramatically. So you can see here's plotted the funding in 2015 dollars as a function of time into the fusion program. The oil embargo had a very large positive impact on investment in fusion. And then you can see that dropping off to less than half what it was after the 90s. So and this is why when I showed that plot of confinement against Moore's law, that last dot was in 1997. So since then, the only major new US fusion facility built has been a facility called NSTX. It's a relatively small, it's not anywhere on the scale of TFTR or JET. And it's actually been down for repairs since 2016. The only other operational major facility is the D3D tokamak at General Atomics. This is where I worked for a few years before I came to Princeton. And this is it's a good facility, but it's was built in 1986. It's not using the newest technology. So this doesn't sound like a great state of affairs here. Probably you expected a more optimistic talk. And but I'm here to say I am optimistic. Fusion research is actually booming right now, and scientists are really optimistic. So why is that? How do I reconcile that?
Good question. Are those inflation-adjusted dollars?
These are 2015 dollars. Yeah. Okay, so a number of things have happened recently that make us optimistic. One is what I'll call the triumph of theory at W7X. So that focus on science has led to new ideas. One of them is in how to optimize stellarators. So progress in theoretical understanding of plasma confinement and the advances in computational modeling let us actually optimize stellarator magnetic configurations on a computer before we build it. So we can now, in principle, design stellarators with tokamak-like confinement. This is great because stellarators don't have a lot of the problems that tokamaks have. If we can do that, that's a big win. For example, stellarators are inherently stable. We don't have to worry about disruptions. They operate continuously, not in a pulsed fashion like tokamaks do. So Germany constructed, based on these principles, based on computational modeling, this new facility, Wendelstein 7X in Greifswald. We call it W7X. And W7X has essentially proved that this works, that we actually can optimize on a computer and get good confinement as we thought we had, which is a triumph of theory. We had never, in the previous 50 years of fusion research, it had all been experimentally driven. You build something and see what happens. Now we have confidence we can start designing things on computers. So this has led to a flood of new science focused on optimized stellarators. W7X is actually a fairly old design. This was designed back in the 90s. With modern computational methods and resources, we know we can do better. So we're getting all these published papers recently about new stellarator designs that people have made on computers that have confinement that is much, much better even than W7X. So you can see this plot shows how many of those fast fusion particles are lost right away when you have a fusion reaction. In W7X, that's something like 30%. In these new optimized designs, it's down below 5%. So you're confining those particles much, much better. You're getting much, much better self-heating of the plasma when it's undergoing fusion. Another breakthrough, which was in the news quite a bit, a breakthrough at JET, so record fusion power at JET. So in 2020, JET went back and made another attempt to operate with tritium to see how much fusion power they could get. In the meantime, between 1997 and 2020, JET had made changes to the facility to make it look more like a power plant. So one of those big changes was JET used to have carbon walls, which is very forgiving, but could never be used in a power plant for various reasons. They moved to tungsten walls, which is probably what's going to be used in a power plant. It turns out for various reasons, it's much harder to operate with tungsten walls than it is with carbon walls. So this actually made it, they were a little hesitant about running with tritium again because they thought the results wouldn't be as good anymore. However, in that meantime, our scientific understanding how to actually operate the device has advanced dramatically. So the net result of that is in 2021, they tried and they succeeded. So they announced 59 megajoules of fusion power in one shot, just a few seconds, more than doubling their previous record in 1997. So this was quite a breakthrough. Now, if you look at how much power we're actually generating in a device like JET, it's not all that much. 59 megajoules could power your house for maybe a day, but it's really dramatic progress from where we had been in 1997. And now you can imagine, JET is a relatively small device. It's not a power plant. You could imagine scaling that up now into something that would actually work. And then one of the things that got probably the most attention in the US is the breakthrough at NIF. So NIF is the National Ignition Facility. It's at Lawrence Livermore National Laboratory. It is funded by the Department of Energy National Nuclear Security Administration, NNSA. So the primary reason for this facility to exist is not for fusion energy research. This is actually what they call stockpile stewardship. The reason this facility is designed the way it is because it's basically simulating how a nuclear weapon will work. NIF features the world's most energetic laser. It's got 192 laser beams that deliver 500 terawatts of power for a few nanoseconds. And you can see, here's the facility. It's something like size of 3 football fields. And then this is all for generating the laser power. And all that laser power is then focused down onto this tiny thing called a hull room, which is the size of a dime. So don't get your fingers in there. So here's a closer look at what's happening. I keep moving this. Here's the hull room. You have your pellet inside the hull room. The lasers are coming in through holes in the top and the bottom of the hull room, and they're hitting the inside of the hull room, generating a huge amount of X-ray power. Those X-rays then are hitting the outside of the pellet, causing the outer shell of the pellet to ablate. That means the outer shell of the pellet heats up and flies off. For every force, there's an equal and opposite force that is pushing that pellet in. The pellet compresses down to a tiny fraction of its initial size, and in that process heats up dramatically, and you get, for a nanosecond, a burst of fusion energy. These experiments are hard, they're expensive. You can see they like to use this, you see this HDC up here, stands for high density carbon, which most people know by another name of diamond. So these pellets are actually quite expensive. This is not a fusion energy experiment. This would never be economically viable as a fusion energy experiment. However, it does provide us now. Oh, I forgot to deliver the punchline here, which is in 2022, they did this and they actually got more power out than they put into the laser. So they had 2.05 megajoules of laser energy hitting the target, and then they got more than 3 megajoules of fusion energy out. So they actually have Q scientific greater than 1 for the first time. So this is the first time a controlled fusion reaction had Q greater than 1. So what does this mean for fusion research? Well, for the first time, Q greater than 1 is not super scientifically interesting by itself. What is scientifically interesting is you have now self-heating of the plasma. You have a plasma releasing fusion energy. That fusion energy is being reabsorbed by the plasma and heating itself more and more. So it's, for a brief period of time, it's a self-sustaining reaction. It's like a little fire. This is the first time we've had those conditions produced on Earth in a controlled way where we have diagnostics and we can measure what's going on. So this is a big deal for scientific understanding. Is it a big deal for fusion energy as in terms of a power plant concept? Well, this concept is not going to be scaled to a power plant itself. So this is delivering the science, not necessarily the engineering. And you can see if we wanted to calculate, well, what is Q engineering in this case? So remember, Q engineering is how much energy into the facility versus how much onto the grid. Well, 0 is onto the grid because we don't have any power conversion facilities. But to make those 2 megajoules of fusion energy, of laser energy, we had to put 300 megajoules into the laser. You know, that's how much it's drawing from the plug. I assume you plug in one of these lasers into the wall. And that's, you know, so you're losing 99% of your energy just making the laser beam. So this is not a fusion power plant concept. This is a scientific demonstration, but I think it was actually worth the hype. Okay, another thing that's getting people excited, ITER. This is a power plant concept. So ITER is the world's next step in fusion experiments. ITER is a massive tokamak that is designed to get Q scientific equals 10. So it'll be generating 500 megawatts for 500 seconds. So this is 250 gigajoules per shot of fusion energy. This is designed on relatively well-known principles. So this is not a big risky device. This is designed fairly conservatively. So ITER is an international project between the EU, which is funding about half of it, and China, Russia, India, Japan, Korea, and the US, who are each in for roughly 10%. This is sited in Cadarache. They broke ground in 2007. The tokamak complex began to be constructed in 2013, and assembly started in 2020. Now you can see, this is a very big tokamak. Here's JET. This is the one we were just talking about a couple slides ago that got 59 megajoules. ITER, the volume is 8 times, the plasma volume is 8 times what it was in JET. So this is a very, very large device. JET itself is a large device. And the construction of it is quite impressive. It's in a huge assembly hall in Cadarache, France. You can see pictures of it here. If you squint, you can see there's little tiny people here below this section of the vacuum vessel. This is one of, I think, 9 sections of the vacuum vessel that we put together. There's some very large cranes, some very impressive things going on in France. It's not a cheap project, but it's a very impressive one. It's the largest scientific project that's ever been undertaken. So the startup date is still uncertain. Likely it'll be around the range 2027 to 2030. It will not run with tritium initially. It won't do that until around 2035. Now, ITER itself is an experiment. It's not a power plant. It has no power conversion facilities, but it is presently the only power plant scale facility that has gone beyond a conceptual design. So this is a big thing for fusion energy research. Now, the foreign fusion programs see ITER as a step towards their demonstration reactors. So the EU has a fusion program, Eurofusion, and they're designing a reactor, an actual reactor that would, demonstrate putting electricity onto the grid. It's called DEMO. DEMO takes a conservative approach, designing around the most proven technology in physics. So EU demo is going to look a lot like ITER will, just bigger. And you can see ITER's humongous and demo is even larger. Other countries like Korea, Japan, China are more or less taking a similar approach. So the US is taking a different approach. And you'll notice all that I've shown, Wendelstein, JET, ITER, these things are all happening in other countries. NIF happened in the US, but that was not an energy experiment. So what are we doing in the US? Well, here's what we're doing. Fusion startups, something that has been in the news quite a lot recently. In recent years, there has been a huge influx of private investment into fusion, especially, not only in the US, but especially in the US. So these startups take a different approach. They don't see these ITER-like facilities as being commercially viable in the US. They're very large, they're very expensive, huge capital costs for these things. Even if the dollars per watt is low, even if you scale it up to a 5 gigawatt facility or something, so you can get dollars per watt pretty low, the large capital costs will make them unprofitable in the US. That's what the startups are saying. So they're pursuing novel configurations, novel technologies that are high risk, high reward to try to get a breakthrough, a disruptive breakthrough that they'll actually be able to make something that's commercially viable. These include things like looking at high temperature superconductors, or looking at hybrid magnetic inertial confinement concepts. So this represents a big change from how we've been doing things in the US over the past 50 years. These startups are willing to take on risk to accelerate the timeline. And there has been a big growth in the number of fusion companies over the past couple of decades. Really over the past few years is when it has accelerated. So this is a plot taken from, they have the fusion industry now has a trade association called the Fusion Industry Association. Last I checked, they had something like 30 members. I think it's more than that now. And you can see over the past few years, this is a plot. I don't know if you can read this, but this is a plot of the number of fusion companies that exist. And this is showing, maybe I should use the mouse. Yeah, that's better. And this is showing when those companies were created. So you can see over the past few years, there have been a lot of them, and a lot of companies that are very large. So at least it's in terms of fusion. So CFS is the largest one right now. It's raised over $2 billion of capital over the past few years. There's other large ones, TAE Technologies. This was one of the first ones. This is raised over $1 billion. ENN is a actually Chinese company. General Fusion is a Canadian company. Helion is in Washington. Tokamak Energy is a company in the UK, and Zap is another company in Washington. So these are large companies. They're getting large investments from various sources, including tech billionaires. So most of this private investment right now is in the US. You can see there's 21 of these in the US, at least at the time of the survey, and a few scattered throughout the world, but really focused in the US. So this private investment is now integral to the program in a way that it never was even just 5 years ago. So previously, all R&D was publicly funded. Now, if you look at the past few years, if you look at the running average of funding into fusion, it's comparable. So the blue bars here is funding from the Department of Energy, and these green lines are the running average of funding from private investment. So it's actually comparable, and this is changing how we're doing fusion research now. So this is changing things because commercial viability is being taken into account from the very beginning. So people are not pursuing concepts that they don't think couldn't be translated into an actual commercial power plant in the US. And because investors are willing to take risks that the Department of Energy, frankly, is not willing to take. If you tell the Department of Energy you want to build something, they'll give you money if you can prove it will work. That's not how it works with these startups. They're giving, this, if it works, then this is what we can deliver. Investors are willing to take that risk. Many of those risks won't pay off. Some of them probably will. This is changing how we're doing work at the national labs. So the national labs are taking a step back from leading fusion power plant design. We're actually giving that to the private companies. They're leading with the design. We're providing support. So we're providing the modeling tools, the theory tools. We're operating test facilities such as NSTX. We're advancing low TRL technological readiness levels. So these are new emerging technologies that a private company wouldn't necessarily want to spend money developing, and supporting, as I said, private reactor design and development. Okay, so what does the future of fusion energy research look like in the US? I've described this a little bit. Let me take a step back to talk about things that have happened in the past few years. So a return to the energy mission. We had stepped back, we had taken a look at the science, and then in 2019, a report from the National Academies of Science, Engineering, and Medicine made the following recommendation. The United States should start a national program of accompanying research and technology leading to the construction of a compact pilot plant that produces electricity from fusion at the lowest possible capital cost. So this was actually a call to change the mission of DOE from advancing fusion science to pursuing the demonstration of electricity from fusion. This was a calling for a big change. Congress and the Department of Energy acted on this recommendation. So a community-wide strategic planning activity was commissioned and completed by 2020. This is something that I was a part of, proud to have been a part of. I think it was successful. It outlined a detailed consensus plan for the R&D needed to achieve a pilot plant. This was all the scientists coming together and saying, if we want a pilot plant, here's what we need to do and here are our priorities. And it recommended broadening the program to address technical challenges as well as the scientific challenges. So NASEM, the National Academies, followed up with another report in 2021, calling for a pilot plant in the 2030s, which is a very aggressive timeline. Remember I said ITER wouldn't even be running with tritium until sometime in the 2030s. And you can see a quote there. This is driven by the needs of addressing climate change. If we want fusion there before mid-century, generating significant fraction of energy for the US, maybe it's not possible, but this is what we would need to do to actually contribute there. So following these reports, there was a bold decadal vision for commercial fusion energy announced by the Biden administration. This was announcing a new initiative to coordinate fusion development across all the DOE program offices. It announced an intention for fusion energy to contribute to the goal of net zero emissions by 2050. And it launched a milestone-based public-private partnership for private companies to develop fusion pilot plant designs. So this was inspired partly by the NASA COTS program, Commercial Orbital Transportation Services, that has been supporting SpaceX. And actually at Commonwealth Fusion Systems, I was talking to somebody who worked there. Commonwealth Fusion Systems is this large startup that was fusion startup started out of MIT. They actually have more former SpaceX employees working there than they do plasma physicists. So they're focused on building something, engineering something. And it has led to more than $1 billion for the first time since the 70s for fusion in the 2024 budget request. So the US fusion program, I think I've explained, is changing. For the past 60 years, we focused on confinement. Now we're confined, that's not done, but we also need to develop necessary technologies. So we need to start developing technology for blankets that can breed tritium, materials that can withstand these high heat fluxes and these neutron fluxes, remote handling technologies that can be used to maintain and replace components in a fusion reactor, and designing and integrating a system, not just one that works technically, but one that can be a power plant that is reliable, accessible, maintainable, and inspectable. So the US fusion program right now is expanding and growing to address these particular things. More material that's focused on material science, magnet technology, engineering, things like that. The US fusion program is starting to take more risks now with potentially high reward by turning a lot of the research direction over to these private companies. So is fusion still 30 years away? This is the question that I always get. I don't have a solid answer for that, but I'll say there's a trade-off between risk and timeline. Relatively low risk approaches, such as the EU demo program, funded adequately, and they're well funded right now in Europe, could see success by 2050. I believe that approach is likely to see success by 2050, meaning electricity on the grid by that time. High risk approaches could deliver something sooner, maybe much sooner. Now, some companies claim that they'll be putting power on the grid in a few years. I think that might be a little optimistic. I'm glad they're optimistic. Others target the late 2030s. I think that's probably more realistic. But I think it's clear there's lots of different ideas. There's lots of things to try. More investment. You can't throw $1 billion at ITER. I should say more than $1 billion. That's small for ITER. You can't throw $10 billion at ITER and get them to speed up the development of ITER. There's just only so fast that they can go. What you can do is you can take more shots on goal. We have lots of different ideas. There's lots of potential for progress in parallel in many different directions. So far, we've only really been developing the tokamak concept. We had limited resources and we were focusing on the most developed concept. There are dozens of concepts to try. And if you look at what the private companies are doing, not many of them are doing tokamaks. A few of them are, but there's a lot of other things that people are trying. Modern computational resources, like we've seen at W7X, this has really been accelerating things. So this is great. Market conditions are sort of an unknown. This will play a significant role in when fusion becomes commercially viable. Even if we can get it technically ready, nobody's gonna pay extra money just for a fusion pilot plant or power plant. So what is that gonna look like in the future? So there's a quote from a Soviet physicist. I think there's some truth to it. Fusion will be ready when society needs it. It's technically achievable. The question is, when will we actually have those conditions when it is necessary? I think that might be sooner than we had thought before, but I'm optimistic. So with that, thank you for your attention. Happy to take questions.
All these hands went up at the same time. So Jim is closest. I'm going to hand it to him. Yeah, Don.
So my question, with all this AI stuff going around, so how do you see the use of AI expediting and helping out?
Yeah, that's a fantastic question. And that's something that all of the scientists have been thinking a lot about, because AI has been really successful in some areas. So there's a number of ways people are looking at to apply AI. One is to actually set the AI loose on experimental data, see if the AI can make sense of what we're seeing in experiment. That's been a little tricky. The experimental data is very noisy. The AI isn't very good. It's at least not much better than a regular, human scientist at making sense of what's going on in the data. The other thing we can use AI though for is to train it on simulation results. So if you have a simulation that takes days or weeks to run, you can do a bunch of those, train the AI on it. The AI will be able to, and then you ask the AI a question about what would that simulation say in this other circumstance. And it turns out the AI can do actually a pretty good job at sort of guessing what that simulation would have predicted. So we can speed up simulations a lot. You might lose some confidence in it, but you can actually speed it up a lot by applying AI in that way.
Online, Bill Tittle.
Dr. Ferraro, thank you very much. This has been a terrific talk, and I want you to know this group has been thinking about fusion, because there are a lot of techie guys here. So my question to you is, why have you chosen to stay working for? This is, I hope you don't take this as rude, but why are you still at Princeton and not one of these startups?
Okay, the question is, why am I at Princeton and not at the startups? Well, that's a fair question. Princeton, so right now, yeah, the startups are exciting places to work. And actually, we've had trouble keeping people at Princeton because, that's providing this, exciting startup culture that's very appealing to some people, including myself. PPPL has resources. PPPL is the Department of Energy's lab for fusion energy. And as such, it has a lot of resources that these private companies don't have at the moment. So we have experimental facilities that are not matched by anything the private companies have. We have computing facilities that are not matched by anything the private companies have. So in terms of having the resources to do science, there's still nothing that beats PPPL or Department of Energy labs. Having said that, it is a government facility. There's a lot of red tape. Things move slowly. And I can see why it's very appealing for many people to go to these private companies at the moment.
Thank you very much. Best
Quick
of luck.
follow-up on that. I was going to ask this anyway. Where does PPPL's funding come from? Is it all the DOE? Does the university put money in? Do you have contracts with any private companies? Do you create intellectual property and license things? What do you do?
Yes. So the answer is yes to all of those. So dominantly, the funding is coming from the Department of Energy. We do have partnerships with private companies. Most of those partnerships are actually funded through the Department of Energy as opposed to direct contracts from the private companies. But the short answer is from the Office of Fusion Energy Science in the Department of Energy is where 99% of our funding comes from.
So I cheated and I snuck in. So we're here.
Hello. That was the best technical presentation I've seen in a long time. The question I have is, you mentioned that the sun has 115 million degrees and it takes 100 in the tokamak. Why is that? And the other is, when you were starting doing your BA and PhD, was like this your dream objective to work on?
Okay, so the first question is, why do we need 150 million degrees in a tokamak or a fusion reactor if there's only 15 million degrees in the sun? And the answer is because we don't have space for the sun on Earth, unfortunately. So the sun is, the sun can take up as much space as it wants. Fusion isn't happening all that fast in the sun. It's a pretty inefficient process within the sun, but the sun is big, right? So it's able to, over that entire volume, it's able to generate quite a lot of fusion energy. We want to be able to generate fusion energy in a small space, a controllable space. And to do that, we need these high temperatures to get reactions happening fast enough. And then your second question was, when I started my PhD, did I envision myself doing this? Is that right? And the answer is yes. So when in college, so I went to Dartmouth College. They have a great plasma physics group there that's focused mainly on magnetospheric research. So solar corona, interaction with the Earth's magnetic field, that kind of thing. So I had taken a lot of plasma physics classes in college. And I was interested in that line of research, but really I wanted to apply it to something where I could, where I felt like I could be really impactful, and energy production, fusion energy in particular, it really drew me into it. So yes, from probably my senior year in college forward, I was most interested in fusion research.
Online, Alan Chenoweth.
Oh, yes, thank you. Really very, very good talk indeed. I have a couple of questions. The first is regarding the tokamaks. You seem to think or imply that progress along the tokamak line came to a stop because of instabilities. But ITER is going ahead with it in a massive sort of way. Have they resolved these instability problems? So that was my first question. Then my second question is, as an old one-time materials research guy, I'm really intrigued by the challenge of what sort of material system you're going to come up with that will withstand the heat and the neutron fluxes and be a tritium breeder at the same time, and not suffer from radiation damage and so on. And those are my two questions.
Okay, thank you. Yeah, really good questions. So disruptions, so large scale instabilities are an existential question for the tokamak concept. And there are private companies and there's ITER, which are pursuing the tokamak concept, and they know this, and this is sort of their highest physics issue to address, the highest priority physics issue to address. Now, there's ways to address them. You can address the forces that are generated during disruption just by your design. As long as you know what forces you're going to have to deal with, you can design it to deal with that. You might not like to have to spend all that money on the steel that you need for it to reinforce it, but you can do it. In terms of the heat loads that are delivered during disruption, there's various systems for mitigating disruptions that people are experimenting on and will be implemented in ITER. So these basically involve, you can detect when a disruption is happening or about to happen. When that happens, you can shoot in a pellet of some kind of material like neon or argon that will radiate like crazy. You send a pellet like that in, and it ionizes and generates all this radiation. And the reason you do that is because the radiation will carry that heat load pretty evenly to the walls of the device, as opposed to when the plasma crashes into the wall, that delivers it very locally and can cause melting. So you try to distribute that heat load as much as you can. So there are ideas. They've been tested to some extent, and ITER will be the real test. ITER has 15 mega amps of current in the plasma. And when that disrupts, it's going to create a huge force, and it's going to create lots of thermal stresses on the vessel. And so we'll see. I'm optimistic that they'll be able to do it. The question is, how reliable will it be? Will it be reliable enough for a power plant, for example? Because you don't want to have to do this every day in a power plant. So as far as materials goes, the leading material for the plasma-facing components is probably tungsten at this point, because it can deal with high heat fluxes. It can get to high temperatures, and it doesn't retain tritium. So this is one of the issues for any plasma-facing component. We don't want it to absorb all the fuel that we're putting in. We want the fuel to stay in the plasma. We want it to keep it separate. But there will be radiation damage for sure because of assuming you use deuterium and tritium. And there are aneutronic concepts that actually don't generate neutrons, but most concepts are using deuterium and tritium, and that will generate neutrons, and neutrons will generate neutron damage over time. So this is a big materials challenge. There are different materials that react differently in that kind of environment. Some of them react in ways that you don't want. Things that include nickel, for example, become activated by that, become radioactive themselves, and you don't want that. There's other materials that can handle it much better. So that is an active area of research. And I would say it has not been down, the materials that would be used in a tokamak plant or any other kind of fusion plant have not been down selected at this point.
Hi, I'm Richard Pavlo. I'm wondering, are you optimistic that the fusion will be able to solve the timing issues regarding environmental change?
I'm optimistic that fusion can play a role. I think fusion is not going to be the solution. If you look at it's not going to be the only solution. If you look at how much power we consume in this country, we would need 1,000 gigawatt scale fusion plants to make up that power. There's no way, even if we got fusion working today, that we could build that many by, for example, the Biden administration goal of net zero in the country by 2050. I think that's going to be, this has been looked at a lot, at the Andlinger Center in Princeton. Other reports have come out. How can fusion play a role? I think it'll be one wedge of our energy production that will be growing in time. I don't expect it to be a dominant or even really significant one before the 2040s, optimistically. But later in the century, you could definitely see, given if the market conditions are right for fusion, you could see it being a dominant source of power at that point.
Online, Mike Katz.
Yes, thank you, Doctor, for a most interesting talk. I guess I'm one of the less technical members of this body, so I find much of this really mind-bending and perhaps amazing. I guess probably not too many of us will be around when it comes online. But my question is, do you know whether any of the private companies that are involved in this research are publicly traded?
Are publicly traded. They're always looking for investors. I don't know if any of these are publicly traded at this point. Yeah, I'm not sure I could give good investment advice here.
I'm not asking for that. Just
one of the challenges is, you can have a good scientific plan and not have a good business plan. And frankly, vice versa as well. You could have a good business plan without having a good plan for actually delivering fusion energy. And the reason is because there are technologies that companies are proposing to develop that can be valuable in their own right, even separate from fusion energy. For example, the high temperature superconductor example I gave earlier. This is some intellectual property that could be valuable even if the fusion mission is not successful. So I think it's not enough when looking at a startup, it's not enough to look at, do they have a credible plan just for fusion? You have to look at, what is their business plan? How do they actually plan to make money? But having said that, I have no expertise in the area, so don't don't ask me on investment advice.
Okay.
I'm Dave DeLong. To what extent is there sharing of intellectual property and information between the projects in the United States, China, Russia, and Europe? And do patents play any role in restricting the development of fusion?
So fortunately, fusion has been very open. I mentioned that fusion research was declassified back in the 50s. And different countries have been working together very cooperatively. This is all, in all the different countries up until very recently, this has all been publicly funded scientific research. So there have been some patents that have been filed. There are a number of patents that have been filed, but these are patents that really would only be enforced if somebody started selling fusion energy, which nobody's doing right now. So patents have not been an issue for, they've not been impeding research, and countries have been very open. Now things might be changing when we get private companies. They're not going to be sharing their intellectual property for sure. So that is something to watch as we move forward.
Stuart Kurtz online.
Yes, thank you. That was a wonderful presentation. I am now convinced that the 30-year timetable of a technically feasible system might actually be available. Not at 100%, of course, but I'm now up to 50%. So one of the things that you mentioned is the difference between technically feasible and economically feasible. And I quite understand that you're looking at the technical feasibility. But my concern with the major question that we have in front of us is that how are we going to deal with climate change, carbon, is that the market conditions are really going to drive it. And if certain sources, not coal, but gas and oil with some countries are so cheap. I remember hearing that Saudi Arabia can produce oil at the order of just a few dollars a barrel. So if that's going to be the case, are we ever going to be able to actually convert over to non-carbon sources if in those conditions?
Probably not. I think there will need to be a price on carbon at some point if we want to take climate change seriously. I don't think that's only true for fusion, but for other non-greenhouse emitting sources of energy. It's never going to be cheaper to produce these than produce fusion energy or fission energy or even wind energy than it is to drill oil out of the ground or dig up coal. I can qualify that. At some point, we're going to run out of those things. If we actually burn through all of that stuff to the point where it becomes expensive, then we probably have gone too far in that direction. So I think, yeah, it's a great point. This has been looked at. There's been a number of people who have looked at, how many fusion plants do we expect to build given plausible costs of fusion energy and plausible market conditions, and they can vary dramatically. If you have market conditions that are set up to penalize greenhouse gases, then it's very plausible that you could get significant power generated within the century from fusion energy. If not, if we don't penalize that, then it's hard to see fusion penetrating the market.
Paul here. Oh, wait. Oh, sorry.
Name is Edward Atkin. Two quick questions. One, I saw in like 2021, there was a lot of public funding, much more than any other year. Also, are any of the other Ivy League schools involved in the fusion research?
Yes, so the spike you saw in that plot was that was Commonwealth Fusion Systems raised $1.8 billion that year. Now that they're not spending it all that year, that's so that plot can be a little misleading. But that was, they raised that money. So they had a high temperature superconductor demonstration milestone, which they hit, that unlocked all this funding from their investors. And now they're using that to build a tokamak called Spark, which is not going to be a pilot plant, but that's their run up to the pilot plant. So that's what that spike was. Other colleges, universities that are working on fusion. Yes, there are a number of them. So we work with Columbia. That might be the only other. You said Ivy League, so that might be the only other Ivy League one. But MIT has a big fusion group. One of the bigger ones in terms of producing graduate students is the University of Wisconsin at Madison, that has one of the bigger fusion energy programs. Let's see, other large ones. Those are probably the biggest ones. UCLA has some. Plasma physics is not something that is commonly offered to undergrads in this country, but there's a few. That might be changing, actually. We hear a lot of students that are actually really interested by what they see. But I should also say, fusion is not just plasma physics anymore. So there's a lot of students coming into fusion from outside of plasma physics now.
Rumor has it that Dartmouth has one or two very successful graduates of their fusion program.
That's true.
Yeah. Online, Alejo?
Thank you for a most informative talk. I might mention I'm a Princeton product, a PhD in '67 in computer science. I have a three-part question triggered by one of your slides. How important is software in the fusion research program? What is it being used for? And a particular interest of mine is programming language. What is the dominant programming language that's used in the software research, in the software for the research?
Well, the answer is software plays an enormous and growing role in fusion research. It's very expensive to build one of these facilities. It's much less expensive to simulate it on a computer. And there was no way we could have simulated these things even 15 years ago. Now we can actually, with the computational resources we have, with the codes that we've built, we can actually do a decent job in simulating many aspects of these facilities. So it's playing a big role, it's playing a growing role. I'm embarrassed to answer your question about the language we tend to use because it's Fortran. But yeah, okay, we got some Fortran fans back here. Don't get a lot of Fortran fans. Yeah, it's Fortran, and the reason is that Fortran optimizes very well. It's we've used it for a long time. I didn't know Fortran before I started doing fusion energy research. I had learned C and C++, and actually for various reasons about how the language is set up, Fortran does very well in scientific computing. So we tend to use that.
Okay, DJ.
Didier Perron, thank you for the lecture. We are in a race for a carbon-free society, and the use of nuclear energy seems to be one of the most important sources of energy. There seems to be a race between fission and fusion. So are you involved, first of all, are you involved with any fission research? And how do you see the future between fission and fusion? Because there seems to be well, not a huge number, there's about 100 fission generator in our country, and you said only 20 of the fusion. So how do you see the future? Because it seems like fission is really taking over the whole thing.
So I don't do any fission research myself. Princeton Plasma Physics Lab doesn't do any fission research. The Department of Energy, of course, does support a fair amount of fission research. So there is a lot of research going on in fission as well, for designing advanced fission reactor concepts. So these would be ones that would be safer, that would generate less waste, that kind of thing. How do I see the future of fission versus fusion? I like fission. I would like to see more fission. It's one of the few sources of power that you could actually imagine taking a substantial fraction of the energy load that we need that is carbon free at the moment. And unlike fusion, we can actually build a fission reactor that will put power onto the grid right now. Fission has some of the same problems in terms of market realities that fusion does, in that fission reactors are very large, high capital cost investments that it's hard to fund in the US and be profitable. Now it works differently in other countries where things are financed differently. And you might see the same thing in fusion. You might see that it's more profitable to build a fusion reactor in France or in China than it is in the United States, just because of how things are financed. But I think if we're serious about climate change, I would like to see more fission being put online as soon as possible. I think over time, I would like to see that ideally replaced by fusion, because fusion doesn't have a lot of the issues that fission does in terms of the potential for meltdowns, the nuclear waste issue, even some of the proliferation issues that fission has. Fusion doesn't have quite those same issues. So fusion has a lot of advantages, but fission is here and fusion is not quite here.
Copy online.
My question is politics hindering the process of the race towards this clean energy production process? Is it too ambitious? Politics is putting the too ambitious plan or not?
Okay, so let me make sure I understood the question. So was the question, is politics playing a role in this?
No, it is playing a role, but is it hindering the process?
Is it hindering? No, I wouldn't say so. Fusion is one of those rare things where politicians on different sides of the aisle seem to agree. It's something that is worth pursuing. They might have different reasons for believing that, but right now there's been a lot of both Republicans and Democrats on the Hill have been supportive of these efforts. So I wouldn't say fusion hasn't really become a political football at the moment. As it gets bigger, maybe it will. That seems inevitable these days. But no, we've had good support from both sides of the aisle, and it appeals to different people for different reasons. It's a clean energy. It's a baseline based. It can support manufacturing, city centers, things like that. Support U.S. energy independence. So right now, everybody loves fusion.
Okay, one more here. Kirk, I say your name.
Kirk Bent, what are the considerations of trying to achieve scale by ganging simpler devices compared to getting bigger and better and fancier ones?
Oh, sorry, I think I missed could you repeat that, please?
Well, you can achieve well, think about it, a computer, you might have a lot of little processors or one big one. Could you gang?
Ganging.
Yeah.
Like a fusion reactor.
Or a bunch of small ones.
So it turns out they tend to scale better. So the larger you make them, the more efficient they are. So it's better to have, in terms of efficiency, it's better to have one giant one than a bunch of small ones. The reason for that is energy confinement. How much energy you can have in the system scales as the volume of the system. How much heat you're losing through the system scales as the surface area of the system. So it turns out the bigger, the better for confinement. And that's why you see things like the demo design that I showed before. That's why those are so enormous. So in terms of just getting to the point where it's competitive cost-wise, I think generally having something larger is better. If we can get to the point where we can make things efficiently operate smaller, and some of the private companies have ideas that might actually work better at these smaller scales, then you could imagine maybe ganging them, having a different setup.
Thank you, Nate. And I think just a comment before we show our appreciation to Nate. I think we're very fortunate in this country to have bright, young, capable, and pragmatic scientists working on such an important project for the future of the country, perhaps not for us, but for our children and grandchildren. So Nate, we have two ways to thank you. The first is with a very formal looking certificate from the old guard showing the orchid, which is our Summit used to be the capital of the orchid business in the US. And we give this to you. And the second way we have of thanking you is with the old guard salute.